Hello, I'm Anna Mackay, and in this video we're looking at decay as a pair with growth and decay within exponential functions. So consider a radioactive substance with original weight of 20 grams, and that's going to decay or reduce by 5% each year. If you've watched the previous video, we talked about multipliers, and so we're trying to work out what the multiplier of this would be. I've already given you the answer there. But if you start with your original 20 grams, if you were to multiply that by 1, what would the answer be? It would stay at 20 grams. So multiplying it by 1 doesn't change it. If you want to increase something, so it's increasing, it would be 1 point something, because something over 1 will increase that original number. So if you want to reduce things, the multiplier has to be less than 1. So it's 0 decimal something, and that 5% is the difference between 1 or 100% if you like. So if you can see, if you added 5% onto that, you'd get back to 1. So we're trying to construct a function for this. So our original is 20 grams. So that letter there is it could be interpreted as a number or a letter. If it's a number, the 0, so it's after 0 years, we have 20 grams. So no time has passed. Or you might think of it in terms of a letter O for the original amount. After 1 year has gone past, so that's subscript 1, what are we going to be left with? So you've got that 20 grams and you need to multiply it by 0.95. So you're reducing it by 5%, but using the multiplier will take you straight to an answer. So we take our original amount and multiply it by 0.95, which is 20 times by 0.95. What about the second year? So you would take what you ended up with at the end of the first year and multiply that answer by 0.95. So there's our W1, the first year, multiplied. And what is W1? Look back up to the last line. It's 20 multiplied by 0.95, and then you're multiplying it again by 0.95, which means you have 2 lots of that multiplier. And because they're the same base being multiplied together, you can add the powers. Each of them was 1, so we get power 2. How many years have gone by at this point? 2 years. And what is the power? It's 2. So that's how they correlate. Going on, after 3 years, you would have the same concept, the original multiplied by the multiplier raised to the power of how many years have gone by. Going on to 20 years, same thing applies. We're down to about 7.2 grams now. And constructing the formula for that for n number of years, we have 20 multiplied by 0.95 to the power of n, provided n is a real number. And the graph of that would look like this. Having a think about the scale we've got here, on the y-axis, we started at 20 grams and decreased from that point. So we've got a little bit more than 20, labelled axis with W for grams as opposed to the y-axis. Instead of x, we have n in terms of years, and that's what a decay function looks like. So let's do one example ourselves. When a diesel electric generator is switched off, the current dies away according to the formula of this, where t is the time in seconds after the power is cut. First of all, we're asked to find I of t when t is these values. Just connecting it to what we've done before, looking at this multiplier here, what's it being reduced by per each t, so each second? If it's 0.25, is it a reduction of 25%? It's not actually, it's the complement of that. It's 75% per minute, per second that it's being reduced by. And what's our original? Well, that's one of the ones that we're about to work out here. So for I of 0, you substitute in 0 where you see t. Let's do that. And our answer for that is, because anything raised to the power of 0 is 1, so we have 24 multiplied by 1, so we're left with 24 amps. I'm going to go on and fill in the other 4 here. Feel free to do that yourself. So before I write the answers, that you can see each of them is raised to the power of t seconds, which matches the number that we've substituted in. And the answers for those are 24, 6, 1.5 and 0.37 amps. Oops, spelling error on the last one there. And noticing that they're decreasing. So we've answered the first question. The second part, what current flowed in the generator at the instant it was switched off? So what might that be asking us? How many seconds have elapsed there? Well, none. So it's at that very instant. So again, that's asking us to work out I of 0. So 24 amps. You might be asking yourself, well, haven't I already worked that out? You have in the part A, but in this worded question, it's trying to get you to understand in words what it is that I0 is. So that's the, some people don't necessarily get that. So hopefully that clicks to you. And being a worded question, it's always good etiquette to answer in a worded answer. When the generator was switched off, it was 24 amps. Next part, we're asked to plot the graph of I of t for t is greater than 0 using the information above. So you would think about your scale that you've got here. We started with 24 amps and we're decreasing. So you need to make sure that's sort of the highest point on your graph. And think about some of the values we've had for t. We had 0, 1, 2, 3. So make sure they're along the axes. We need to label our axes, not x and y in this case. We've got I and t. Always good to write what the units are for those two. And we're going to plot the points. So I of 0 was 24. I of 1, so after 1 second, we're down to 6 amps, and so on, plotting our 4 points and connecting the dots. And there's our graph there. And label your function. Don't leave that line on its own. Give it a name. And then our last part here is use your graph or technology to find how long it takes for the current to reach 4 amps. So again, asking yourself, is that 4, is that a t or an I value? T is time. This is not 4 seconds, it's 4 amps. So that's in place of a y value, which is on the y-axis here. So looking at the graph here, we're interested in finding 4, going along until it hits the function, and then reading off that t number, how many seconds. So you can see it's less than 1.5. So let's work this out using our technology. So you're going to graph this function. This is the function of I, and I've substituted that in. Instead of a t, I'm obviously using x. Again, using your view window to match what we've got here, it approximately looks like this. Just a tip, if you're ever having to graph one of these yourself, please, when you see something that's asymptotic here, please make sure you can always continue to curve down. Please don't get your ruler out, and because it looks like it's getting straight at the bottom, that you finish it off with a straight line. That's not correct. It will never be constant. It will always be decreasing microscopically from point to point. And what we're doing here is we're finding the intersection of y is equal to 4. And using your calculators, you would now write in a sentence, you go back and read the question, find how long it takes. It takes 1.29 seconds for the current to reach 4 amps. I'll leave you to write that in a sentence. That's the end of this video. Give it a thumbs up, subscribe to the channel, and the next one in the series is the natural exponential e to the power of x. Thank you.